Okay, so root mean square speed. All right, so you can be asked to calculate the root mean square speed of a gas. And what this gets at is mean is for average, and you're square rooting, first you're rooting and you're squaring the speed, so it kind of undoes what you're doing. The reason for mean, the reason for average, is that we have a sample of gas, the particles are all moving at different speeds. When you look at an animation of a sample of gas, or if you actually could have some high-tech equipment, see the particles, you're going to see that some of the particles move very slowly, some are moving really fast. It forms what they call that Maxwell distribution curve, where you're going to have some particles moving at very high speeds out here, some particles moving at very low speeds down there, right? So there's a distribution of speeds, fast to slow, most going in the middle. So they actually add up all these speeds, take an average, and that's your average speed. The reason it is root square, like why are they squaring then square rooting and doing it, that takes out the direction. So really what we need to know for root mean square speed is there's an average because there's a bunch of different speeds of particles. We need to know that. We need to know that root mean square speed depends on temperature, because as things are hotter, they're moving faster, they have more average kinetic energy. And also things with a greater molar mass move more slowly. So root mean square speed is something we don't talk about a lot, so it's one of those things that you may forget when you're taking the AP chemistry test, which is okay because you get this sheet for the test. And you can say, I don't know root mean square speed, but they're asking about a gas. Go to the gases section, I go down, and it actually says mu RMS equals root mean square speed. Okay, so well here equals that. And then on the other side of my sheet, it tells me the equation for root mean square speed. Okay, it's a good thing I have that musical filler there for my thinking time. Root mean square speed, I'm going to use the equation 3RT over M. Okay, the things to remember here, we'll see when our units cancel out. The molar mass is in kilograms per mole, and that's because our R gas constant is going to be joules per mole Kelvin, and a joule is actually equal to kilogram times meter squared per second squared. So you'll see that you need kilograms here to deal with the kilograms here, and the Kelvin will cancel out too. Here you can see that this number becomes larger when the temperature is greater and particles move faster. We see that in animations. And this number becomes smaller when molar mass is smaller. And that's because a heavy thing moving slowly has the same amount of force as a slow thing moving very fast. Getting hit by a smart car versus getting hit by a semi. Depends on which one is moving faster. They could do the same amount of damage. Okay, so let's do some calculations. It says calculate the root mean square speed. Oh, hold on, that is right. Sorry, I want the square. Root mean square speed, whoops, of helium and nitrogen. So we'll do one, then the other, at 25 degrees Celsius. You will need to know that 1 joule equals a kilogram times a meter squared per second squared. So accelerating the kilogram a meter per second squared. Right? Okay. So, so I already know root mean square speed. The thing I'm looking for, I'm going to solve for helium. Okay. It equals the square root of 3 times the R, the gas constant. So that's 8.31, and that is joules per mole Kelvin, and that's going to be times 298, because it's 25 Celsius, I'll add 273, 298 Kelvin, and my molar mass is going to be, it's helium, and helium, if I look it up, is 4.0026, and this is grams per mole, right? So that's 4.0026 grams per mole. To turn that into kilograms, I can say there's 1,000 grams for every 1 kilogram. So I go 1, 2, 3. So 0.00426 kilograms per mole. Okay, so that's the molar mass of the helium. 0.00426 kilograms per mole. All right, so now let's do some stuff with the units, because right now I have, when I cancel out my units, the kilograms won't cancel out. I'll be left with joules per kilogram. And that's a weird way. Actually, I'd have the square root of joules per kilogram. That is a very weird way to describe speed. So I'm going to mess around with those units a little bit, but let's zoom in. Right now I have joules per mole Kelvin. Okay, I know that 1 joule is equal to kilogram times meter squared per second squared. So I'm going to substitute, instead of joule, I'm going to put in kilogram times meter squared per second squared. Alright, so that's my new unit for my R constant. So let me fit that in here. Yeah, I'm going to have to actually erase this whole thing. It's not a very fine eraser. Not much detail. Okay, so kilogram meter squared per mole Kelvin second squared. So now, let's cross out units because I like it. Kilograms is gone, moles, kilograms per mole, gone on both sides. Kelvin gone, Kelvin gone. I have meters squared per second squared. I'm going to square root that and get meters per second. Yay, I like describing speed that way. That makes more sense in my brain. Okay, so this paper doesn't have any answers for calculations. This one does. So I'm going to go ahead and multiply this guy all the way across and divide by that. And when I do that, I get a very large number. So if you try that first, you're going to get a large number. Don't worry. I get 1,743,000 or 744,000 actually, and some stuff, right? And then when I square root that, I actually didn't round until the very end, because that's better practice. When you square root, you get 1,320. And at this point, it was still meters squared per second squared. When I square root it, it becomes meters per second. And then I look at sig figs, 2. So I'm just going to say 1,300 meters per second. All right, so that is the root mean square speed of helium. I think I'll just tell you for the nitrogen. Oh yeah, we'll do it. Okay, for the nitrogen, I'm going to go ahead and just plug it in. So this is going to be for helium. All right. And if I'm going to do this for nitrogen, the only thing that's different is going to be this molar mass. So I'm going to be a cheater and just erase my answers and plug in the nitrogen's molar mass, because it's still 3 times the gas constant times 298, because it's still 25 degrees Celsius. And the nitrogen is going to be 28.014, but it's kilograms, so it's really going to be 0.028. 0.014. Yes. Okay. So when you type that in, so I do this whole thing, before I square root it, I ended up with the square root of 265,194 meters per second. And when I square root that, I got, and rounded to 2 sig figs, I got 510 meters per second. Okay, I kind of wanted to do the second one too, just so we could say when nitrogen and helium are at the same temperature, they have the same average kinetic energy, right? Because temperature is an indicator of average kinetic energy. And I can see that the helium is moving faster than the nitrogen, and that makes sense. For them both to be hitting walls of a container with the same force, helium, which is tiny, has to move faster than nitrogen, not as tiny. Root mean square speed. Yeah, you know, we have time to actually fit in effusion too. So, it's going to make a separate video. Rate of effusion. Effusion is a gas that's going to be escaping through a small hole. So, like, you know, if you have a balloon, there's a gas in here. Rate of effusion is going to be how fast the gas escapes through this small hole. For rates of effusion, again, you can use this, our sheet. It doesn't actually, I don't think it does. It does. It says R equals rate of effusion. So you look over and find an equation that has rates, and it says rate 1 over rate 2 equals square square root of the molar mass of 2 over the molar mass of 1. So they're inverted because the heavier a gas is, the slower it's going to effuse. It's moving more slowly, so it's less likely to hit, it's not going to hit the hole as often and get out. Also, it's actually a larger gas, it's a heavier gas. So we know the larger the gas is, the slower it effuses, so you have this inverse relationship. So the inverse of the molar mass will give you the rates. So just make sure 1 up here has to be 1 down there. The greater this molar mass is, the slower the rate of effusion is going to be. Okay? So let us try one. Tetrafluoroethylene, C2F4, effuses through a barrier at a rate of 4.6 times 10 to the negative 6 moles per hour. An unknown gas effuses through the same barrier at the rate of 5.8 times 10 to the negative 6 moles per hour. What is the molar mass of the unknown gas? Okay, so I'm going to use this whole rate 1 over rate 2 equals square root of molar mass of 2 over molar mass of 1. And the thing I don't know is molar mass. I'm going to make this my unknown gas. Okay? So I'm going to put molar mass of 2 as my unknown thing. So the molar mass of this guy, just add it up, and you're going to get 100.022 grams per mole. All right, and then for rates of effusion, I'm going to get, let's see. Oh, okay, so 4.6 was for this gas, so it's going to go up here. 4.6 times 10 to the negative 6, and that's mole per hour. Okay, and then let's see, I've got 5.8 times 10 to the negative 6 moles per hour. That's the rate of my unknown gas. Okay, so I'm going to do this divided by this, and when I typed that in, I got 0.7931 equals second molar mass over the known molar mass. Okay, so now I'm going to square root both sides. Sometimes people do this out of order, so that's why I'm doing step by step. So now I'm going to square root both sides. When I square this, that side I get 0.629 equals, this when it's squared I just lose the square root. I'm going to get that unknown molar mass over 100.0022, right? Yeah, I think so. Grams per mole. And now I want to get the molar mass 2 alone, so I multiply both sides by 100.022, and I find out that that second molar mass is going to be 63, when I round to 2 sig figs, 62.915, but I round to 2 sig figs because of these rates. These rates have 2 sig figs. 63, this was grams per mole. Okay, so the thing here, the C2F4, weighed 100 grams per mole and effused this fast. The unknown thing was smaller and it effused faster. So those seem like reasonable answers to me, so I'm happy and therefore done.